Lecture 2.5, Differences between Temperature, Heating, and Internal Energy. Since this is a physics course, physics understanding is always the central focus. A good question to ask is, what is the difference and connections between temperature, heating, and internal energy? So before we get to this question, let's write down a couple of things. Temperature and the zero law of thermal. The zero law of thermal. This essentially defines what a thermometer is. The everyday definition of temperature is a measure of hotness or coldness. Unfortunately, it's not so easy to define temperature. This statement refers to one type of heating called specific heating. So when that statement is made, that's what we mean. But we're going to talk about this later on in the chapter. So in this type of heating, what we say here is that the transfer of specific heating is from high to low K micro regions, where in exchange of K micro occurs. So when I say that this exchange, this is by that statement that I've been saying. This is the workless transfer of energy. There is no work, but you're transferring kinetic energy. So just to be clear here, this is the zero law of thermal. And what it does here is it really gives us a definition of a thermometer. And it reads like this. If two systems let's call them A, B, and AC, where A is the same in both, are in thermal equilibrium, what do I mean by thermal equilibrium? There's no exchange of kinetic energy. Then B and C are also in thermal equilibrium. So picture-wise, what would I draw? I could imagine that I have two blocks. Let's say that one of these blocks is warmer. No, doesn't really matter. And this other one, let's say, is right here. So these guys are in contact. So this is A, this is B. And then what I'm going to compare them is to another block system where, again, here's A, and then this one here is C. So this is A and C. So if these guys are in thermal equilibrium, then it implies here that block A is a thermometer. It's a material that tells us that they're in thermal equilibrium. Now, other than that, it's not that really much more than that, but I can say that there are three common temperature scales. And they're Kelvin, Celsius, and Fahrenheit. I believe this is HEIT. I should have been a little bit more careful. And when we look at these scales, here's our temperature scales. There's something that's really important. Now note that because of this, of course, there's transformations from one temperature scale to the other. So if I'm talking about Kelvin, this is the temperature of Celsius plus 273. I can convert Fahrenheit into Celsius, or vice versa. But the key thing that I want you to realize, and this is important for calculations, and what's important is that the change in Kelvin is the same as the temperature change in Celsius. In many problems, people will convert Celsius into Kelvin when they didn't have to do that. And what you're seeing here is that the reason why I have this picture is that look at the difference between these two. That difference is 100 degrees C. Clearly, this difference from here to here is also 100 degrees C. So the difference between Kelvin and Celsius is this translation of 273. So again, this is really important for calculations. So what I want to do here is that I want to look at phase. So what determines the phase of a material, and when I talk about the phase, I mean a solid, a liquid, or a gas, depends on their internal energies. So the key player is micro potential energy. So if I look at the micro potential energy, well, if I have a solid, solids have large potential energies. And so typically what that means here is that they typically have stronger bonds between the molecules. On the other hand, if I have gases, have ideal gases, that is, zero potential energy. So in other words, we're talking about no bonding for ideal gases. So the thing that we need to look at is liquids. So when you look at liquids, they are in between potential energies, which what you'll find here is depending on the liquid, you're going to see that you'll find here that bonds, many of times, bonds connect and disconnect constantly. So what I'm going to do here is that I'm going to show you the FET applet. So I want to go to the FET applet states of matter. Applet. And what it does here is it really shows very well this. What do I mean by this internal energy thing here? So here we go. So what you're seeing here is that I can make, so if you look at this applet, one of the things that you see here is that I have the ability to add heat or cool something off, and I can read the temperature. But what you're seeing with the solid here is that you get this sort of like structure that you have sort of like the packing fraction is very tight. And you could see that there is some microkinetic energy, but the dominant term, without any doubt, is the potential energy. Now, if I look at liquids, you could see that liquids, particles can move, but there is some cohesion between the molecules. So there is a connect and disconnect. And then finally, if we have gases, well, if it's an ideal gas, which this isn't because they're colliding, what you're finding here is that there's no bonding whatsoever here. So what we should do here is that when I go and I look at this guy, I just want to show this briefly, and let me go back to what I want to do here. So I'm going to go back to my screen. Now, what I want to do here is that I took images of these guys, and so I want to copy them. So here's my images of all three states of matter. So I'm going to paste this in. And what you're seeing here is that in this case, this is a solid, this is a liquid, and then this is a gas. Now, what we're finding here is that in this case, if I look at the internal energy, now remember, the internal energy is right in here. What is the energy associated with that guy right there? And what we're going to see here is that a big part of the internal energy is that their micro potential energy is large, whereas their macro kinetic energy is small. Now, if I look at a gas, note that the gas, it only has micro. It has no potential energy at all. So now, if I look at a liquid, what you're going to find here is that their micro potential energy is small, and their kinetic energy is also relatively small when you look at the internal energies of these guys. And one of the key things that you should really look at the spacing between the solids and the liquids. Very, very little difference in the bonding distance between them. So now that I got the phase, now we should go back to our original question. There are deeply held misconceptions. In everyday language. And that's why I wanted to do this lecture right here. So there's deeply held misconceptions of everyday language in thermo. We need to address these. Okay, so now we start with the question that I asked the title of this chapter. What is the difference between temperature, heating, and internal energy? That's what we really want to address right there. So the first thing that we should do is we should talk about classical temperature. So I've sort of said what temperature was up to this point. I do want to say here is that I will tell you that when I first understood what actual temperature was, I was quite shocked. Temperature is much more complicated than what we have been saying up to now. So what I do want to do is that I'm going to plan on going through temperature in stages to try to get its meaning across to you. So here's what we have to do here. So to really understand temperature, I need to make some definitions because I've been using the definition of temperature very loosely. So then I'll say that when dealing with a random moving ideal gas, the average velocity is exactly 0. And of course, the question is why? If a gas is truly random, then at any moment, gases have opposite velocities. And what I mean here, so if I focus on just one moment, let's say that I have these 4 particles here, and what I mean here, maybe this particle is going like this, but note, I could have components in that direction from other gas particles, or I could have particles coming inwards like this, and as I start to sum these velocities, because of this, the sum of these velocities will be exactly 0. Because of this reason, we use a different kind of average. And this is called the root mean. Oops, let me do this better. It's called the root mean square. And this is what we defined as RMS. So what you're going to see here is that many a times you'll see me say that RMS, and I'll still call this the average. It's not the traditional average, it's a type of average. So if I say average, I really mean RMS. So here is the classical temperature. So when we say the word, the classical temperature, you're going to see that that's in this course, I'm just going to say temperature. And what this tells us here is it's proportional to KRMS, which is equal to 1/2 MV RMS squared. Now, this is a very interesting definition for the following reason here. What this really tells me here, that temperature is really the translational kinetic energy of a gas. So when we move on to more complicated gases like diatomic or polyatomic, they also rotate. Rotations do not contribute to the classical temperature of temperature. They only the translational kinetic energy does. Okay, so now that we defined what temperature is, here I go. So let's start with the first one here. So the thing that we want to do here is temperature is not a measure of internal energy. Now, I know I'm going to be talking about materials. It's really a measure of U micro plus K micro, where K micro is the total kinetic energy. And the total kinetic energy is then N times Krms. So we can look at an example. So I imagine that I have a cup versus a pot of boiling water. And then, of course, the question is going to be, which contains more internal energy? Well, if I think about a cup, I could imagine that I have a cup. And so if I look at that, here's going to be my cup, and I have boiling water in there. And this has a temperature of 100 degrees C. Now, if I have a pot, and then let's put some handles on this thing. Well, this pot also has boiling water. So when I look at this thing, this is also at 100 degrees C. Clearly, this has less water. This one has more water. So what we're seeing here is that they have the same temperature, because it's proportional to the RMS kinetic energy, but different K micro, which we already said is the total one. So this K micro must be KRMS. So then if I look at this thing, we can clearly say that if I have less water, then that means I have less water molecules. So then that tells me that I have a small number of molecules. So therefore, it has less internal energy, excuse me, less K micro, because it's equal to this of the cup times KRMS. But if I have more water, then I'm going to have more molecules. So then if I look at the pot, I have a much bigger N value. So therefore, I'm going to have more K micro, which of course is bigger because of the number of molecules. So in this sense, this clearly separates temperature from internal energy. So temperature and internal energy are not the same. Now let's talk about specific heating here. So specific heating is the energy transfer from high to low kinetic energy regions, right? That's what we mean by high. So let's look at this thing just to be careful here. And there's some key points. And I think this is where a lot of misconception comes. So the first key point that I want to talk about is that it says once heat transfer is done, heat ceases to exist. It doesn't occur anymore. So picture-wise, how do I actually show that? Well, let's look at boxes again. So let's say that I have a box here, and I have another box here. And what I'm going to do here is that I'm going to transfer heat from one box to the other. So in this case, the red represents the high kinetic energy region. Let's call this A, let's call this B. And what I'm going to do here is that I'm going to transfer heat in that direction. So this guy has high kinetic energy. This one has low kinetic energy. So when I reach equilibrium, what do I mean by equilibrium? What I mean here is that when I look at my boxes, what I'm seeing here is that now they have the same kinetic energies. Excuse me. So if I look at block A and I look at block B, what I'm saying here is that they have the same Krms, which is proportional to temperature. So in other words, heat is now zero. So what I'm really saying is that there is no more kinetic energy transfer, and heat ceases to exist. I know I said this twice, but this really, a lot of people confuse this, what we mean by heating. So what I'm really saying here is that matter does not contain heat, but it does contain K micro. So I'm going to move this down just a tiny bit. Just a tiny bit. So this is a really sticky point in everyday language. And I would say that very strongly, everyday language is wrong and misleading, very misleading in regards to heating. Just listen to this language here, right? Let's say that it's cold in your car or in your house, and you'll say, turn on the heat because the car is cold. That doesn't make any sense. Another one is, let's say if the temperature outside is, let's say, 100 degrees Fahrenheit, which is about 40 degrees Celsius, and we're talking about weather, I should have said that earlier. One says this heat is oppressive. So, and the reason why we say terms like this is that this language is rooted in the past, when people believed heat was already contained within an object. It's not. It is not in an object. It is the workless transfer of energy here. So then I believe I have two more things that I want to talk about. Heating causes changes in internal energy. And we've said this numerous times. So what I'm going to be looking for is I'm going to be talking about heating. And this heating, that this is what changes the internal energy. We're not talking about work where more complex materials have complicated internal energies. And what I mean by this is that since we're going to be talking about materials in this chapter, and then going back to the ideal gas law, that means that when I look at the internal energy, I have to include the potential energy now. So besides the potential energy, which is different for every atom, we're going to have K translational. That's 1/2 mv squared. And then I'm going to have K rotational. That's 1/2 I omega squared. And then I could have even K vibrational, which is 1/2 K x squared. So the terms become more complicated. Once again, the reason why we study ideal gases is that there is no potential energy, and we only look at the translational. So when we look at the translational only, this is what tells us about ideal gases, because we wanted the simplest material possible. So the last thing that I want to talk about, which I think is interesting, is we could say here is that the temperature energy model of thermal has two extreme temperature values. And here's one of them. One is that there is a lowest possible temperature. And this is what we talked about in lab. Classical physics or classical thermal claims, and I should say in theory, that all molecular motion stops at absolute zero. And what we did here is that in lab, we had this plot that we did. We plotted temperature and pressure. And what we said here is that if we have a line like this, that at the location right here, where pressure is equal to zero, that tells us this is minus 270 degrees, minus 273 degrees Celsius. So when we look at this absolute temperature at 0K, this reads 273 degrees Celsius negative, and in Fahrenheit, it's 460 degrees Fahrenheit. So they're saying that that is the lowest limit. Well, what do we know about this? Quantum physics shows that theoretically and experimentally, it is impossible to reach 0 degrees, 0 Kelvin point. The world's lowest temperature region, or temperature record, I should say, is this. They got 38 trillionth of a Kelvin. And that means that this is 38 times 10 to the minus 12 Kelvin. But this, of course, is not 0 Kelvin, right? So this is the world record here. And so what you're finding here is that this was done by a German team I forgot when it was. I think it was like in 2010, using a Bose-Einstein condensate. And if you really want to, this is called a BEC. If you really want something to read that's interesting, look at the connection between Bose and Einstein. really, really gorgeous history behind that. This clearly shows that there is a lower bound into temperature. So then the next one that we want to talk about is we want to talk about the highest possible temperature. Special relativity shows that as the speed of a particle approaches the speed of light, which is typically abbreviated as c, it requires an infinite amount of work. In other words, if I look at the limit, and if I use the work energy definition, that as the speed of a particle approaches c, this is proportional to a limit that really looks like this. That's going to be 1 minus v squared c squared over 1, and then this approaches infinity. So what does this mean here? Well, this means no massive particle can reach the speed of light, because you have to do an infinite amount of work. That doesn't make any sense. So what do we know here? So there's a place called Brookhaven National Laboratory at Brookhaven National Laboratory, and typically it's known as BNL, has a relativistic ion, no, let me be careful, heavy ion collider. That accelerates two heavy ions at each other. So in this case, what they do here is that they will take two gold ions. They have no electrons, and they smash them together. And as a consequence, you generate an enormous amount of heat here. Okay, so what you'll find here is that this is what happens. So these are gold atoms or gold ions. Okay, these are gold ions. And when they collide each other, man, their temperatures are crazy. So what they get here is that this collision generates a temperature of, and so this is the T highest temperature ever recorded, of 4 trillion degrees Celsius. And it turns out that it's about 10 to the 12 Kelvin. So that means that this temperature here at this collision region is 10 to the 12 Kelvin. Well, is this temperature infinite? Right? So we should ask, is this temperature infinite? And the answer, of course, is no. 10 to the 12 is not equal to infinity. But I will tell you this, that at the start of the universe, that is the Big Bang, the temperature is estimated to be 10 to the 42 Kelvin. So I guess that, could I get, an infinite temperature limit? No, because if you reached, anything that reached 10 to the 42 Kelvin temperature, then you create another universe at that point. So there is an upper limit, I guess. How do you get to that? I don't know.